Tutorial 3.2, Question 1. In Question 1, we are supposed to prove a certain reduction order formula for a particular integral. In this case, you have the integral in equals to x to the power of 2n e to the power of x. So to do such a question, we want to use the by parts method. In doing by parts, we have to choose to differentiate one term. I choose to differentiate this, and then to integrate the other one. So in performing by parts, I keep what I want to differentiate, I integrate what I want to integrate, minus, within this integral, I will differentiate this to give me this one, and then I will integrate this. So I've done one round of by parts for question 1. And for this question, you need to do a by parts a second time. And this time, again, I want to actually differentiate this expression and to integrate this. So once again, by parts, I keep this term and then I integrate the e to the power x. Minus, I differentiate this. To differentiate this, the 2n is left unchanged. I bring down the power and then copy the same. The power is now less 1. And I integrate e to the power x, which is just e to the power x. Now I'm left with tidying up this expression. This is minus of this, which is here, and minus is a plus. And what I'm doing here is I'm going to rewrite this thing as 2 bracketed n minus 1. I have factorized out the 2. So in so doing, you will realize that this expression is actually your I of. This expression will therefore be just I of n minus 1. And this is question 1 of tutorial 3.2. Okay, an overall picture of this question 1 of tutorial 3.2. Now let's move on to the next question, question 2 of tutorial 3.2. For this question, the same thing is going to happen. I intend to use by parts again. Sorry, not by parts, sorry. For this question, I don't need by parts. I could actually integrate this expression, the I1 of 2 part 1. I could actually integrate this expression directly using this formula. It might be new to you, but this formula is very useful, and I would like you to actually learn this formula, that whenever you have to integrate e to the power fx and you have a f prime x by the side, this one can be integrated straight away to give you e to the power fx. If you ask me why is this true, you simply need to differentiate this once and you get this integrand right away. So for this question, for finding I1, I intend to use this formula. So what I'm going to do here is I've rewritten this as like this. I've introduced a minus 2, and so I neutralize it with a minus half. Why do I do so is because then this expression here is exactly the form of f prime x e fx. Why is it so? Because if you see here, this is minus x squared, right? If I differentiate minus x squared, this is minus 2x. So now I intend to actually integrate this expression to give me e to the power of minus x squared. And then I put in the limits. In putting the limits, I'll just get this. And then I tidy up, I get this expression, which is quite straightforward. So let's take a look at the first part of number 2. Moving on to part 2, we now start off with I of n plus 2. Right, we want to prove that I of n plus 2 is a certain expression. I of n plus 2, by definition of the question, is actually this. So in this case, I intend to now show that this integral will work out to be what the question wants me to prove. For this question, you need a simple trick. you break this x of x to the power of n plus 2 into power n plus 1 and the x. Why do you think I want to do this? The reason for breaking up into this manner is because then I can integrate this one directly. Remember, we have seen this expression earlier on. Now, having written in this form, I now intend to use by parts again. I keep what I want to differentiate. When I integrate this, using the formula that I just learned, this integration actually becomes this. So integrating this one gives me this expression minus. Now, bear in mind, if you have a limit, you must subject the first expression here to the limits as well. Minus integral of 0 to 1, I differentiate this expression, I get this, and now integrate this, I'll get this. And then now you have to apply the limits to this first part here. You put x as 1 followed by x as 0, you get minus e minus 1 over 2. Right, because inputting x as 1, this gives you 1 to the power of n plus 1, which is just 1. This gives you e to the power minus 1, and this is minus 2. When putting 0, it comes up to nothing. Then over here, minus and minus gives you a plus. Then n plus 1 and the 2 gives you this expression here. And then whatever remains is just x power of n e to the power minus x squared, you can see. And then again, you realize that this one is just your I of n. So I have successfully proven what the question wants me to do, and that's to show that I of n plus 2 is equal to this. And then moving on to the next part of part 2, it now wants me to find I of 5. So to find I of 5, I basically use the proven formula. The proven formula says I of 5 becomes minus 2 1 over e, putting n as 3. Right? Why is it 3? Because you look carefully. When n is 3, this will be 5. And then this will be 3 plus 1, which is 4. Then divided by 2, you get 2 here. Then this is 3. So my I of 5 therefore works out to be here, based on the formula that I've just proven. And then I now apply the same formula again to I3, the same formula that I've proven to I3. I get this. How do I get this? I just put n as 2, sorry, n as 1. Why is it n as 1? You look carefully here. This is I of n plus 2, right? I just need n to be 1 to give me I3. So I put n as 1. Then become 2 over 2, which is 1, I1. That's how I get 2, I1 here. And then I1, remember, I1 was actually computed earlier. I put back the I1 as what we had computed earlier. And then I got to this line, which tidies up to be this. Okay, let me tell you what's going on in this calculation again. This minus 1 over 2e combines with 2 times this to give me minus 3 over 2e. Then 2i1, right? 2 times i1, and this is your i1 here. And now you further tidy up this expression to give you this, which is actually the answer. And this is my question 2. Moving on to question 3. In question 3, you are given a hint. It asks you to first and foremost differentiate this expression. This expression can be differentiated using so-called the product rule. Differentiate keep plus keep this. You differentiate this expression. How to differentiate expression? Bring down the power, copy the same, power less 1 times differentiate the inside, which is 1 over x. So upon tidying up, writing this on the left, upon tidying up, this is here, this expression, the x here and the x here can be cancelled off, leaving you with this. So upon tidying up, I get this entire line. So someone may ask, why should this be a hint or help? With this expression here, the next thing that do is you want to integrate this entire expression from left to right. Integrating this on the left, if you integrate a differential, you get back itself. You see? Integrate this is here, and integrate this is here. So upon integrating this throughout, it will help us later on in our next part of the question, and that is to prove that okay, in this part of the question, we want to prove something concerning I of n plus 1. So okay, this line is actually a rewritten form of this line. I have simply moved this to here so that I can write this on the right. You can see I moved this term to the left and I wrote everything all on the right, and this term is just here. Okay, so how does this expression help me in the next part? And here you go. Now to integrate 1 plus ln x power n plus 1, which is exactly this expression. According to what we have proven, this becomes just like this. You can see. Now bear in mind that this one has to be, you need to apply the limits to this first expression. It's very easy for you to forget. Because upon integrating this, right, upon integrating this, whatever you have, you're going to apply the limits to it. So in particular, this first term, right, you need this limits. And likewise for this, you also need this limit 1 to e. And what you see here right now is, upon putting the limits into this expression, I get this. And this one tidies up nicely to be just in. So this is actually question 3, the proving part. Let you have a good look. And now we want to do the later part of question 3. Okay, this one, if you know a simple trick, it'll be very easy. You want to integrate from 1 to e of this expression. What you can do here is you break this 5 into 4 and 1. 4 times this expression, right, will give you this. You see? And then 1 plus ln x times 1 plus ln x squared will give you 1 plus ln x cubed. So the reason why I'm doing this is because, having done so, you'll find that this is exactly 4i2. 4i2. And this is your i3. So now to evaluate this expression, I first and foremost use the proven formula to reduce i3 into this. This line to this line is simply making use of what you have proven earlier here. This one. By putting n as 2, I will be able to get i3 as this expression there. So you realize that I didn't compute i2 yet. Okay, so I have this expression. Now I combine this to i2 to give you i2 here, and then this is over here. 2 cubed is 8. Now I apply the formula that we've proven for on i2. I get this, and then applying the formula to i1, I got this. So from this line to this line, what happened is I've combined these two together, and minus 1 minus 1 give minus 2 is here. So this minus 2 I1, right, is minus 2. This whole thing is actually I1. And then tidy up to become 8e plus 2i0. I0 meaning this. Now I've deliberately written as power 0 here to tell you that this is actually I0. But if you look carefully, this is actually just 1. Integrating 1 of an integral like this, right, is just e minus 1. The upper limit minus lower limit. And then tidy up to be just 10e minus 2. And this is your question 3. The later part of question 3. Let me put it like this for you. Hope you can see. Okay, now moving on to question 4. Equation 4, once again, we are asked to prove a certain reduction order formula. This time we have In equals to the integral of cos power nx. This expression is the same as writing as cos x whole thing bracketed to the power of n. Say again, this is the same as writing as cosine x bracketed whole thing to the power of n. And this expression can also be rewritten as cos x whole thing to the power of n minus 1. So I want you to notice that this expression is identical to this expression, is the same, alright? You have to get used to this. So I will write this as like this, and now I want to perform once again by parts. I intend to, in this case, integrate this expression and then differentiate. You're going to differentiate this one, right? So in the case of by parts, the one that you want to differentiate, you keep it as it is. You integrate cos x, you get sin x, and not forgetting the limits. Minus pi over 2 to pi over 2 minus integral dx. Within here, right? I want to differentiate whatever I want to differentiate. Can see is here. Differentiating cos x to the power of n minus 1 is here, right here. And then if you integrate this is sin x. So integrate this and then you differentiate this one, I get here. Alright, now then if you apply the limits to the first part, if you put in power 2 into this expression or put in minus power 2 into this into the x values, you find that they will all add up to nothing, 0, right? You put in power 2 here, and after that put in minus power 2, you find that in either case they will add up to 0 because cos of power 2 or cos of minus power 2 is actually 0. Now for over here, I can just tidy them out. You have a minus here, you have a minus here, so it now become a plus. The n minus 1, sine and sine gives you sine square, and then cos power of n minus 2. And now the trick lies here. I rewrite the sine square. I intend to write the sine square as 1 minus cosine square. In rewriting this, and after that I expanded it. I take this times this to give me this, and I take this times this to give me this. You can see 1 times this is itself cos square times cos n minus 2, right? This will give you power n, right? It just add up the powers. And now what we have here is this expression is actually I of n minus 2, and this one is actually I of n. So what we have here is In is equals to n minus 1 of In minus 2 minus n minus 1 of In. I bring this thing to the left. I bring n minus 1 In to the left, and then I'm going to get just I of In, and then this stays on the right. Then bring the n down, and I get the proof that In is equals to n minus 1 over n of n minus 2. So this is actually part A of number 4. Okay, you can see. And now moving on to 4b. In the case of 4b, we have a little bit of a tedious calculation. 4b is here. Okay, in the case of 4b, the first part of 4b is you are trying to write down in, right, into in terms of n. You're trying to rewrite this in terms of n. Now, what we have so far proven is in is equal to this, right? And then if you use this one recursively, right, you will find that if you use this expression recursively from in equals to n minus 1 over n of I of n minus 2, you use it recursively, you will get this if n is odd, and you will get this if n is even. So I want you to realize that in these two cases, right, one of them, when it's odd, it ends with I1. When it's even, you end with I0. When it's odd, you have 2 over 3, you end with 2 over 3. If it's even, you end with a half. Now, it can be quite difficult for beginners to see that it should be like this. So what you ought to do is, you should actually try out with, say, I7. Right, you try with I7 first for odd number, okay? You can try I7 first, okay? If this is 7, right, then this becomes 6 over 7 I5, right? And I5 is 4 over 5 I3, and then I3 will be 2 over 3 of I1. Can you see? So you try a small number, you realize that when n is odd, you will end with 2 over 3 of I1 at the end of it, when n is odd. Likewise, when n is even, to see that you end up with this, right? You try with some small number, say for example, you try with I6. I6 will end up with 5 over 6 I4, right? And I4 would be equals to 3 over 4 of I2. Can you see? 3 over I2, and then I2 will be equals to 1 over 2 of I0. So by using small number, you will realize that in the case when it's odd, you will end with 2/3 I1. When case when it's even, it will end with 1 over 2 of I0. You will see that this is the case. Now, you want to bear in mind that when n is odd, these numbers on the numerator, they are actually even. And when n is even, this number on the numerator, actually they are odd numbers. Alright? And of course, in this case, when n is even, the denominator will be even. And again, when n is odd, this denominator will be odd. So actually, writing down this in into two different odd and even is not too hard if you just look at simple cases like I7 and after I6. Alright? Then you want to note about I1 and I0. What is I1 equals to? I1 means to integrate from this to this of this one, sorry, I0. I0 means you have cos x to power of 0. So I0 means this. Cos x power 0 is actually 1. So to integrate 1 dx for this limit, you will end up with just pi. On the other hand, I1 means cos x power 1. To integrate this one is just sine x, and then you put in the limit, you just get a number of 2. So you must know that in this calculation, right, after I've used the formula recursively to say that In is this when n is odd and this when n is even, you have to know that I1 and I0 are computed as I1 and I0 here. One is pi for I0 and 2 for I1. Okay. Once you have reached this stage, right, the rest of the steps beneath is just arithmetic tidying up or arithmetic manipulation. Okay, it's simply as that all the reduction order, all the by parts are already done, right, and all the integration are already done. So from this point and down, to express In in terms of n is simply algebraic manipulation. So let me go on from here. Okay, let's say for this one, right? For this one, okay, let's see. Okay, I'm going to show you. Okay, for this one, right? For this one, I have on the numerator, right, n minus 1, n minus 3, n minus 5, and so forth, right? On the denominator, can you see the jump? So what I do is I intend to actually fill in the gap on the denominator with the missing terms. You can see the n minus 1, the n minus 2 on the denominator, so that I get a complete series of number, which I can then express the denominator as n factorial. Can you see? Can you compare the denominator of this and the denominator of this? I've just padded in enough terms to make the denominator n factorial. As much as I added this extra term on the denominator, I have to actually do the same thing to the numerator, and that's why it resulted in n minus 1 square, and then n minus 3 square, n minus 5 square, 2 square, right? And so on. Okay, so in the case when n is odd, I'm just rewriting this into this form, and the reason why I'm writing this form is because I want the denominator to turn out to be a n factorial. And likewise, in the case when n is even, I'm going to do the same thing for the case when n is even, starting from n minus 1, n minus 3, n minus 5, and so forth, right? So what I'm going to do is I'm going to put in enough terms so that the numerator, right, can also be written as a factorial. So what have I added in? I've added, see, okay, compare this, right? I've added n, I've added n minus 2. Can you see? N minus 2 wasn't here, right? I added n minus 2 and n minus 4 and so on and so forth, right? I put in this extra term on the numerator so that I'm going to get a factorial, n factorial on the numerator. So for the denominator, I likewise paddle in the same term and I get square, n minus 2 square, n minus 1, and so on and so forth. Right? So this is just simply algebraic manipulation. And then from here, okay, if you're able to see, right, this denominator is simply n factorial. Can you see? And over here, right, this numerator, is simply n factorial, right? Then these terms, right, these terms, because when n is odd, right, these terms, if you look carefully at these terms, are actually even. Okay, so like this one, like even, this is even term, 2 square is even term. So throughout the numerator, what I'm going to do is I'm going to take out all the 2's. This is, I'm taking out 2 square, and then also n minus 1 square, n minus, sorry, for this one, right, this is an even number. I can also take out 2 square from here. I can also take out 2 square from here. I can also take out 2 square from here, and then of course 2 square from here, and then I'll be left with 2 to the power of n minus 1. Why is it n minus 1? Okay, so there's something that you want to ponder. Why is it to the power of n minus 1? If you look carefully, right, from n minus 1, n minus 3, n minus 5 until 2, right, you actually have only m minus 1 over 2 of such numbers. But because of square, it becomes n minus 1 over 2, and then squared, it just gets 2 to the power n minus 1. Okay, so if you see it, good. If you can't see it, you just be patient and slowly write down, say, using the case when n is 7. Then you can see what I'm trying to say here. And then this 2 to the power n minus 1 when combined with 2, right, will just give you 2 to the power of n. And then you're going to have this factorial. This factorial comes about because after you take out 2 from each of this, right? Each of this, it becomes just n minus 1 factorial. Okay, so again, you need to have the eyesight to see it, Yeah, it's quite tedious. But actually, to express in terms of n, theoretically, actually, this would have sufficed. Okay, would have sufficed. Just replacing the I1 and I0 with 2 and pi. Actually, this expression is already enough. Just that we're just tidying up. It's just a matter of tidying up. So you can see it good. If you can't see it, maybe try a bit more. You can get it eventually. So likewise for this other one, you have the same thing that I told about. You paddle in to make sure the numerator is a factorial, and then the denominator, right? Denominator, okay. For the denominator, right? For the denominator, if you were to take out all the 2's, like 2 square from each of them, right? You can get 2 to the power n, and whatever does remain, right? You can get just n over 2 factorial, and then because of square, that's why I got square here. Okay, so I do recognize that I'm saying too fast, but it takes a little while for someone new to this to slowly grapple with this by using small numbers. So you can try with, say, I8, when n is 8, and slowly figure out that this will be this, and this will be this. So you get a nice expression like this, and in the later part of the question, you're asked to find I of 2016. So because n is even, right, you just apply this formula, you plug it in, you get this expression for I of 2016. So for question 4b, right, it is quite taxing because of the arithmetic, right? So once again, you're using this formula recursively to get to this one, and this one when n is odd and even, right? I do recognize that this question 4b is a bit taxing, right? Okay, so with this, we come to the end of question 1 to 4 of tutorial 3.2. There's actually another video to show you question 5 and 6. There's also on the table, so you can actually go and take a look.